Study Unit 2, Lecture 1. This lecture will focus and provide a brief overview of power resistors. In power electronics, a power resistor, or just a power resistor, is any resistor where the intended use will require the resistor to dissipate more than 1 watt of energy. There are several uses of power resistors in power electronics, but they are either used as a current limiting device or as a purely dissipative device, in other words, a device which is used to dissipate energy. In terms of power electronic specific circuits, power resistors are used in series RC networks, in series inductor resistor networks, RC snubbers, current sensing, resistor dividers, voltage and current damping, and so on. Depending on the application, there are several resistor types which can be used. There are carbon resistors such as carbon solid ceramic resistors and carbon deposited film resistors. There are metal resistors such as metal thin film, metal oxide film, glaze thick film, so on. Then there are also wire wound resistors, which is basically just a wire wrapped around a cord. In general, almost all power resistors are cylindrical in nature, using a central core with the resistive element constructed around the central non-conductive core. Important properties of the core are that it is very thermally conductive, in other words, can conduct heat very well, is impervious to moisture, has to be chemically inert, and is able to withstand thermal shock. In other words, if the temperature of the core cycles rapidly, the core should not break in any way. In the example shown here, each of these resistor types is constructed around a core. There are then the terminals, which are used to connect the internal parts of the resistor to some external circuit. And finally, all power resistors will have some or other casing, which is dependent on the application of the resistor. The resistor terminals are normally made out of nickel-plated steel, or in certain cases brass, and are force-fitted to the core to make contact with the resistive element inside. The first resistor that will be considered is what's called a metal glaze thick film construction. The first step to making this type of resistor is to deposit some or other resistive material onto the central core. This material can either be a cracked carbon film, a glaze of glass powder which has been mixed with other metal compounds and then baked onto the core. A very precisely controlled thin film of a metal alloy can also be deposited onto the core. And finally, a metal oxide, or rather a tin metal oxide resistor film can also be deposited onto the core. The thickness of material, the actual geometry of the core, as well as the composition of the material used to make the resistive layer will determine the overall resistivity of the metal glaze thick film resistor. Once the material has been deposited onto the core, a helical groove is precisely cut into the material, and this helical groove is used to tune the resistance of the resistor. What is essentially happening by cutting the groove into the material is that the overall length of the resistor material is being increased. A disadvantage of this technique is that it significantly increases the inductance of the resistor, which is an important factor in power electronics. Molded carbon composition film resistors are manufactured in a similar way, but there is no helical groove cut into the material, and the resistivity is instead controlled by precisely controlling the thickness of the deposition as well as the content of the material which is being deposited onto the core of the resistor. An advantage of this approach is that because there is no helical structure around the core, the inductance of such devices is very, very low. For applications which require very high power ratings, typically in the range of a few hundred watts, then wire wound resistors with an external heatsink can be used. Wire wound resistors make use of a central ceramic core with a high tensile strength wire wrapped uniformly around the core. Although such devices have a relatively high inductance, they are able to withstand significant rapid cycling, both thermal and electric. A fourth type of resistor construction is the solid carbon ceramic resistor. These are manufactured by baking and pressurizing finely ground powdered clay, alumina, or carbon into a resin. By controlling the carbon content, the resistivity of the resulting tube of resistive material can be controlled. An advantage of this type of construction is that it has an inherently low inductance, but is also mechanically very robust because there's no structural helical composition inside the resistor. It is just one homogeneous piece of resistive material. This homogeneous construction gives it a high transient voltage, inherently low inductance, high thermal capacity, and of course finally mechanical robustness. The disadvantage of the solid carbon ceramic construction is that the devices are quite brittle, so any direct hard mechanical impacts will damage the device. In an ideal world, the voltage and current relationship around the resistor is given by Ohm's law, which simply states that the voltage over the device is the current multiplied by the ideal resistance. This is of course not true, and the resistance is a function of the voltage across it, the frequency of the signal switching through the resistor, and the temperature. The resistance of the resisting element is given by the length of the resistance divided by its area, multiplied by its resistivity, which is again a function of voltage, frequency, and temperature. What this means in practice is that as the frequency of the sinusoid switching over the resistor increases, its performance as frequency increases will also decrease. So simply put, if the voltage switching across the resistor increases in frequency, the overall voltage seen across the resistor will decrease. A common way to represent a more realistic resistor is to use this model shown here. This model incorporates an ideal resistance as well as an inductance and a capacitance, which models the inductive and capacitive properties of the resistor. There are three factors which are important when considering the electrical coefficients of a resistor. There is the coefficient of linear expansion, the temperature coefficient of resistance, also sometimes designated with alpha, and then the voltage coefficient of resistance, which is often represented by phi. If the resistor is operating at a low frequency, the temperature and voltage coefficients of resistance are often included as a weighting factor to the base resistance value. It is important to note that although from this equation there is the implication that the resistance as a function of temperature or voltage varies linearly as the temperature or voltage changes, the values of alpha and phi are just approximations and may not necessarily follow a linear relationship. This can be seen in this graph from the reference text. The actual variation in resistance as a function of temperature follows a quadratic function as opposed to a linear one. As with the temperature coefficient of resistance alpha, the voltage coefficient resistance phi is also not necessarily a linear or even a quadratic function. For example, here phi is defined as 0.62 multiplied by the resistivity to the power of 0.22. These types of values are derived empirically for a particular resistor, and the designer must consult empirical data tables in order to determine what the voltage coefficient of resistance is for a particular resistor under certain operating conditions. The maximum working voltage, or V hat, is the limiting element voltage that may be continuously applied across the resistor without the resistor failing. The maximum working voltage can also be thought of as the maximum voltage that will develop across a resistor family as long as the power rating of the resistor is not exceeded. Another way that this can be thought of is that in some family there will be some critical resistance where the voltage which develops over the resistor is not limited by the resistance or the current, but by the maximum working voltage. Above this voltage, flashover will occur where electricity will literally jump from one terminal of the resistor to the other. Once again, the maximum working voltage is defined empirically and may be defined differently for different types of resistor families. Finally, a resistor will have what is termed a residual capacitance and a residual inductance. The residual resistance, or rather residual inductance, will increase as both the resistance and the power rating of the resistor increase, whereas the residual capacitance of a resistor will increase as the pulse rating of the resistor increases.